All right, it's finally time. So, talk about some tangent planes and linearizations, but we're first going to start talking about the tangent lines because really they're essentially the same. Just the tangent plane kind of has an extra little piece that's going to be very natural to think of once we talk about it. So, the equation of a tangent line, very generically, it's y minus the y coordinate equal to the slope, which is the derivative at the point. So we can say it's f prime at x naught times x minus the x coordinates. It's a very general equation of a tangent line. And then the linearization is really the same thing, except we write it slightly differently for God knows why. So the linearization, like this is a word when I type it, it always thinks it's being misspelled because it's just like not a word. It's recognized sometimes. So this is the tangent line approximation. It's really just the equation of the tangent line again, written in a different way to our function f of x at, instead of the point x naught, y naught, for some reason we say at x equal to a. So at x equal to a, it's really just the same equation, but we're going to rewrite it. So instead of y minus y naught equal to f prime of x naught times x minus x naught, we're going to write y minus, well, y naught is f of a. It's equal to the derivative, which now we're going to write as f prime of a times x minus a. But we're really not going to write it like this. We're going to rewrite it. We're going to isolate y. So we're going to write it as f of a plus f prime of a times x minus a. And instead of calling it y, we're going to call it L of x. L for linearization. So other colors. Here's your f of a, which would be like your y naught over here, and your f prime of a, which is like your slope, or your f prime of x naught. Same equation, just a slightly different way of imagining what's going on. And if you recall, you might have used linearizations back in 17a to say approximate the value of something like the square root of 8. In fact, let me remind you. So let's use a linearization to approximate or estimate the square root of 8. And just from the get-go, I'm thinking, okay, I know that 9 is kind of the closest nice square number, so this should be a little bit less than the square root of 9. So we should get something a little bit smaller than 3. Let's actually do it though. So first we're going to find the linearization. In fact, actually, before I get going here, I should draw some stuff. Yeah, let's maybe. Let me write some words. So yeah, we're going to linearize the function f of x equal to the square root of x at the nearest good value, meaning the nearest value that's easy to substitute into that function, which is going to be 9. And then we'll use it to approximate square root of 8. So we're just going to throw the formula at it. So our formula, our linearization, again, I'm writing it again. You probably don't need to write it again. It's going to be f of a plus the derivative at a, or the slope, times x minus a. Our a is 9. Our function is the square root of x, so writing things over here, our f of a is going to be the square root of 9, which is 3. Your a value or the point you're plugging in should always be relatively easy to evaluate. That's kind of the point. And then our derivative, well, our function is the square root of x. Our derivative of x to the 1/2 is 1/2 x to the negative 1/2, or I would prefer to write it as 1 over 2 times the square root of x. Whatever you like, though. So then f prime of our point 9 is going to be 1 over 2 times the square root of 9, which is 1 over 6. So the slope of our tangent line is going to be 1/6. So we can rewrite this equation as our linearization L of x is equal to f of a, which is 3, plus our slope, which is 1/6 times x minus the x coordinate, and our a value is 9. Make sure your a looks like a and your 9 looks like 9. Graphically, here's what we've done. So we've taken our function, the square root of x, which looks like it usually looks. Here's your good old square root function. Maybe exaggerated slightly. And at a equal to 9, with a value of 3, we have found the equation of the tangent line. So right here, that tangent line, that's your L of x equal to 3 plus 1/6 times x minus 9. Useful piece of information. It's almost always a bad idea to simplify this. I'm leaving it like this on purpose. I don't want to multiply out the 1/6 and combine the terms. No, this is how you want it. And the reason is because we're trying to use this to approximate the square root of 8. So I'm going to go over here, I'm going to plug in 8, and the idea is that instead of getting that y value there, that would be the square root of 8, we're going to go up just a little bit higher to the point on the line because it's much, much easier to plug in 8 to that linearization and get a relatively easy thing to calculate at, which will be pretty close to the actual square root of 8. Let's see. So if I say, well, and so I'm going to write a few more things here. I'm going to point out that this L of x is an approximation of the square root of x, at least when we're close to 9. If we move too far away, not a very good approximation, but close to 9, really good approximation. So then I can say that the square root of 8 is approximately the linearization evaluated at 8, which is going to equal 3 plus 1/6 times 8 minus 9, or 3 minus 1/6, which normally I would like to write as a mixed fraction. It's going to be 18 minus 1, 17 over 6. But I feel like that's not super helpful when it comes to actually like knowing how good a job we did. So if you actually write it as a decimal, 3 minus 1/6 should be what? 2 point something. 2 point, I think it's 8333 forever. Yeah, that sounds right. 83337. Whereas if you use a calculator, the square root of 8 is approximately, I think, 2.82. So pretty good, right? At least good to one decimal place. That's not bad for just doing something not too terrible. So that's the idea of a linearization / the equation of a tangent line, is we can use it to approximate things, and it's a thing that's easy to calculate things for, like plug numbers into, that's a good approximation of the actual function near the point of interest.
Would they tell you to subtract the answer you got by the order?
Sometimes you're asked to find the error, yeah, in your estimate versus the actual value. It's not something I typically like to do, but yes, that's a thing we could be asked to do. So let's now extend this idea to a three-dimensional version where instead of a curve and a tangent line, it's going to be a surface and a tangent plane. And the nice thing is the equation is going to be practically the same as it was. So that's what we kind of talked about already. So here is the 3D version. Blue, sure. Let's see. So yes, the tangent plane to the surface, which I usually think of instead of y equal to f of x, we're thinking of like, say, to the surface, I'll just, yeah, z equal to f of x comma y. At the point, instead of x naught, y naught, it's going to be x naught comma y naught comma z naught is given by, in fact, let me grab the other page here just so you can see how similar these are going to look. So here's the previous tangent line equation. Tangent plane equation is going to be z minus z naught equal to the partial derivative with respect to x evaluated at x naught y naught times x minus x naught. So a slope times an x minus x coordinate plus the other slope, partial derivative with respect to y, still evaluated at the coordinate x naught y naught times, I'm sure you're not going to be surprised, y minus the y coordinate. So really, really, really the same idea, right? It's a derivative times the variable minus the value. It's a derivative times the variable minus the value, and then the other derivative times the variable minus the value. but really the same idea. You're just adding on an extra dimension here. Cool. So, okay, and then the linearization is the same idea where we're gonna isolate z, we're gonna call it L of xy instead of z. So the linearization is gonna look like L of x comma y equal to, instead of z naught, we're gonna say that z naught is f of x naught comma y naught. Right, we're adding z naught to the other side. In fact, just so everyone feels comfortable with this is your z naught plus the same stuff that's already there. Fx at x naught comma y naught times x minus x naught. Sometimes people leave off the parentheses x naught y naught and just say it's fx times x minus x naught plus fy times y minus y naught because the meaning is still there. So fy at x naught comma y naught times y minus y naught. So not much of a leap from the tangent plane equation to the linearization equation. Questions so far? We pass around the tendency. All right, so let's actually do some things as opposed to just talking about equations. So for example, we could say, let's find the linearization of the function f of x comma y equal to x cubed times y to the fourth at the point 2 comma 1. That's part A of this question. So yeah, I'm looking at this and I'm gonna say, cool. So my f of x naught y naught. Sure, I'll write this down this way. So my linearization of xy is equal to f of 2 comma 1 plus fx evaluated at 2 comma 1 times x minus 2 plus fy evaluated at 2 comma 1 times y minus 1. Probably an unnecessary step. Like I feel like you probably don't need to write that if you're actually doing this problem. I think it makes more sense to find the stuff and then plug it in. Whatever. So let's see. So off to the side here, my f of 2 comma 1 is going to be 2 cubed times 1 to the fourth, which is 8. Fx, the partial derivative with respect to x, is going to be 3x squared times y to the fourth. And then when we plug in, our fx at 2 comma 1 is going to be 3 times 2 squared times 1 to the fourth, which is 12. Similarly, our fy partial with respect to y is going to be x cubed times 4y cubed. And when we plug in 2 comma 1, we're going to get fy at 2 comma 1 equal to 2 cubed times 4 times 1 cubed, so 32. Cool. Now let's go jam everything into this equation. So this is going to tell us that our linearization at x comma y is equal to, let's see, 8 plus 12 times x minus 2 plus 32 times y minus 1. And although you might be tempted to, you really, really don't want to multiply this out. Right? I don't want to say this is 12x minus 24, this is 32y minus 32, and then combine all the constants. And the reason why is because it's harder to do the next part usually if you multiply it all out. It's easier to leave it like this. So the next part of this question, so that was part A. The next part of this question, which yeah, I shouldn't try to just squeeze it in there, is to then use this linearization to approximate the function evaluated at something close to that. So for example, we want to then, why is there a staple? Ah, that's the problem. There's an old paper in here. Haha. Something funky there. Okay. So we're going to then use the linearization to estimate f of, what have I got here? 2.2 comma 0.9. which would be 2.2 to the third power times 0.9 to the fourth power. Not an easy thing to calculate without a calculator. Like, not impossible. Like, this is totally within the realm of you could actually probably multiply it out. It'd be a bit tedious, but if you really had to, you could figure out 2.2 cubed times 0.9 to the fourth. It would just be gross. But we have calculators, fortunately, so we'll just look at it at the end. So all we're going to do is we're going to say, well, and I don't think you have to write this next part, but I think it's really useful. I think it's useful to say, hey, remember the function f of xy, we are approximating with this linearization. That's the whole idea. In fact, the idea here is that this function, I don't know exactly what this function looks like, but whatever it might look like in 3 dimensions, I'm going to graph something that's clearly not it because I don't need to draw it. But let's say your surface looked something like that. It's clearly not what it's going to be. But then you've got like this, say, this point of tangency at x is 2 and y is 1. And so then you're graphing or you're looking at this tangent plane that's tangent at that point right there. And you say, okay, well, if I move just, like, if I move a little bit away from x being 2 and y being 1, which again, haven't drawn very well, but okay. I'm just going to move like over here to 2.2 and 0.9. And so then I'm going to be like up here a little bit away from the surface, but that's okay. That's the whole idea. So this is an approximation, which is then equal to what we said it was, 8 plus 12 times x minus 2 plus 32 times y minus 1. So then we can say, oh, but then I want this. So my f of 2.2 comma 0.9 is approximately my linearization evaluated at 2.2 comma 0.9. And then we just plug those numbers in and we get 8 plus 12 times 2.2 minus 2 plus 32 times 0.9 minus 1. And this is why you don't want to multiply it out first. Because if I multiplied it out, I would have had 32 times y. And 32 times 0.9 is not easy for me to do in my head. It's much easier for me to do 32 times negative 0.1. I know what that is pretty easily. So here we're going to get 8 plus 12 times 0.2 plus 32 times negative 0.1. That's looking like 8 plus 2.4 minus 3.2. That's going to be 7.2. How good of an estimate was it? Good question. I don't know why I feel like I need to pull out my handheld calculator when I literally have a computer in front of me, but I do. So let's see, if we plug that in, we end up getting 2.2 to the third times 0.9 to the fourth. 6.98. Okay, not too right? We're not that far off. So I'll just point out that f of 2.2 comma 0.9 is approximately 6 I guess I should round up to 6.99. So yeah, again, a decent estimate. Let's see what else have I got on the docket here. Sure. Okay.
One.
Okay. Linearizations, whatever. They're fine, they're useful. I think we're more interested in talking about the tangent planes. So let's go ahead and actually do the other thing where instead of finding the linearization, we're going to find the equation of the tangent plane, or should I say the plane tangent to z equal to 4x squared minus y squared plus 2y at the point -1 comma 2 comma 4. I don't know if I've ever been in any classroom where the air just feels like it's always on, but okay. I guess that is what it is. All right, so similar process to what we just did. We're going to find the partial derivatives. We already have the z naught value. So I'll point out this is your x naught, y naught, z naught. Honestly, if I'm doing this kind of question, I'm going to write down the formula first because I don't actually know what I need to be doing until I've written it down. So I'm going to be like, cool, I know I need z minus z naught equals fx times x minus x naught plus fy times y minus y naught. I will point out I did leave out that it's fx evaluated at x naught, y naught. I don't think you have to write that part. If you really, really like it, you can use a vertical line here and say, oh yeah, we're going to be plugging in -1 and 2 for x and y. And here we're going to be plugging in -1 and 2 for x and y. It's another way we write that you're plugging in those points. Okay, so I got to find some things here. So let's see. My z naught is 4. My fx, take the partial derivative, I'm going to get 8x minus 0 and plus 0. So my fx evaluated at -1 comma 2 is going to be 8 times -1, which is -8. Why don't you all find fy and then find out what you get when you plug in -1 for x and 2 for y.
Okay, that is the original equation, is the z actually two y or just,
So one more time.
is z, two y on the third coefficient?
That is, yeah, 4x squared minus y squared plus 2y, not zy. For me, you can usually tell the difference between a 2 and a z because the z will always have a little crosshash and the 2 will not. Although my 7s do, so watch out. Let's see here. My partial, notice I'm using f here and I didn't write f anywhere here. Again, the assumption is, right, this z, I'm also thinking of as f of xy. It's a very natural shift or change or thing we do. So let's see, fy is going to be -2y plus 2. And if we plug in -1 for x, there isn't anywhere to plug it in. Plugging 2 for y, we get -2 times 2 plus 2, which is -2. All right, I think we have all the pieces we need. So we're going to go ahead and write our equation as z minus 4 equal to -8 times x minus minus 1. Let's write x plus 1 plus -2 times y minus 2. And that's probably a sufficient place to leave it at. Like you could totally leave it there and it's technically correct. This one I probably would actually do the simplification because we're not being asked to use it to estimate stuff. So I might rewrite this as z minus 4 equal to -8x minus 8 minus 2y plus 4. And then bring everything to one side. So you have positive 8x plus 2y plus z minus 4 minus 4 plus 8 is 0. So just equals 0. That's how I would write it. It's kind of the standard way when you put all the variables on one side. It's also perfectly standard to isolate z and write it as just z equal to -8x minus 2y. They're both the same thing. They're both the equation of a plane. How do we know it's the equation of a plane and not some other surface? I don't know. How do you know? How do you know that this is the equation of a line and this isn't? Or this is the equation of a line and this isn't? I would say the defining characteristic is that for the linear things, the lines and the planes, all of your variables are raised to what power? This one, right? All your variables are the, or not there at all, right? You could have a plane where you didn't have an X or a Y, possibly, or a Z. It's totally possible. But all your variables aren't to any powers other than 1 or 0, I guess. Whereas equations like this, definitely not straight lines, or in 3 dimensions, not planes. Okay. Should we do this one? Well, sure. Yeah. What time is it? 1:35? Okay. Yeah, we can do this one's ugly. I guess sometimes you have to do the ugly ones. Okay, sure. Let's look at this last linearization tangent plane sort of deal, and then we will move on to talking about the chain rule. All right, so a model for the surface area of a human body, of the human body, is given by here's the function. So capital S is equal to f of w comma h, and it's very gnarly here. The numbers are 0.1091 times w to the 0.425 power times h to the 0.725 power, where w is weight measured in pounds and h is height measured in inches.
That was an absolute function.
A what function? Oh, like an absolute, like those are absolute value symbols. I can kind of see that. Yeah, just a good old one. Um, and S, then the units for S is in square feet. S is square feet. Or I suppose I should say it's area measured in feet squared. Bless you. All right, let's see. So I think it goes without saying here, but I'm gonna say it anyway, that if you didn't have a calculator, plugging things into this function would be really, really challenging, right? Something to the 0.425 power, that seems real, real dumb. But we have calculators. So also the kind of dumb thing about this problem is we're gonna do linearization and you're still gonna need the calculator to do the linearization part because the numbers are still not pretty even afterwards. So what's the point? Good question. I don't know. The point is to practice doing the thing, I guess. So part A, let's find the linearization of the function s when the weight is 160 pounds and the height is 70 inches or 5'10". All right, so usual process. We know what the equation we know what the equation looks like, and I still feel like I need to write it down. It's just how I would do it. Like not for you all. I'm really just saying I know kind of what I'm supposed to do, but I really don't say I want the linearization. I'm using W and H instead of X and Y. It's going to be I guess my just see, I don't even know what I'm doing. It's my f of W naught comma H naught plus my partial derivative with respect to W times W minus W naught plus my partial derivative with respect to H times H minus H naught. Okay, now I have a better idea of what I'm doing. So let's write down my partial derivatives, which are going to be real gross too. My FW, my partial with respect to W, is going to be 0.1091. The derivative of W to a power, I'm just going to use the power rule and get 0.425 times W to the 0.425 minus 1, which is going to be negative 0.575 times 8. Good, who thought of this question? It's probably in the book, actually.
Yeah.
Some textbook writer thought of this question. Similarly, your partial with respect to h is going to be also gross, 0.1091 times w to the 0.425 times 0.725 times h to the that minus 1 is going to be negative 0.275.
From that, or
Where's that?
for the F.
So I did the power rule. So the derivative of w to some power, you bring that power down, and your new power is that old power minus 1. And 0.425 minus 1 is negative 0.575. Unless I'm subtracting wrong, which I don't think I am. Okay, so then, yeesh. All right, so we plug it all in, super gross. So my linearization at WH is going to be this function evaluated at 160 and 70. So, yeah, 0.1091 times 160 to the 0.425 times 70 to the 0.725 dish plus my f delta. Oh my, sorry, this is inappropriate, I feel like.
This is a good reason why we use
Right, exactly. So it's my 0.1091 times 0.4025 times 160 to the negative 0.575 times 70 to the 0.725 plus this piece over here, which is my FH, so my 0.1091 times my W, which is 160 to the 0.4025 times my 0.725 times my H, which was 70 to the negative 0.275. Absolutely terrible. Simplifying this, we get that our linearization is going to be, I'm going to say equal to, even though I'm approximating some stuff here. This number here is about 20.524 plus 0.546 times W minus 100. Oh, I forgot. Oh, I forgot some pieces here. I forgot here the W minus 160. And I forgot here the H minus 70. Jeez, too much going on. So this part here is about 0.546 times W minus 160 plus this is about 0.231. 213, apologies, times H minus 70. So interestingly, I think maybe if you plug in 160 and 70, these both are zero, and a regular, normal, I don't know what kind of people they use to gather this data, but an averageist person weighing 160 pounds and having a height of 70 inches would have about 20 square feet of surface area. I mean, I guess so. I don't know. Feels like a lot, but maybe not when you really start measuring things. I mean, well, I don't know, square foot's like kind of like this is not far from a square foot, I guess. 20 of these, maybe. Who knows how good this model of body surface area actually is. And then you could use this linearization, although I don't think we really need to approximate the surface area of a person weighing a different amount and having a different height. Like say someone was 165 pounds and was, I don't know, 72 inches tall. How much surface area would we estimate they have? Well, instead, it doesn't seem like this is a problem where I feel like the point is totally lost, right? The whole point of doing the linearization was to make the calculation easier. That is not happening here, right? Plugging in those numbers to this first thing is a much less horrific process than plugging those numbers into this grotesque thing I wrote over here. So linearizations are nice when they make the calculations easier. When they don't, I kind of fail to see the point. Now, the tangent plane is still a useful thing that we're going to use when we start talking about directional derivatives. But that's kind of most of the reason I think we're talking about it. This idea here, not so wonderful, I feel like. But someone decided that they wanted you to do a thing, so they said, do a thing. Okay, how much time have I got? Clearly, I did. All right, let us continue forward. Let's talk about the chain rule. So specifically, the chain rule for multivariable functions. Because I imagine all of you at least have heard of, hopefully remember the chain rule from 17a, where like you took the derivative of the outside function, you left the inside function alone, then you multiply by the derivative of the inside function. Also, pretty sure Dedell's first like discussion sheet had a whole bunch of chain rule-esque problems on it. Let's see here. Yeah, like it's funny the way he wrote these questions, I think, but sure. Yes, he definitely had you find some derivatives of things that would require the chain rule. Right. Okay. I feel like question five. So I don't know if you remember these questions, but I feel like question five is written in a really kind of interesting way. Find a function whose antiderivative is given by this. That's just a really roundabout way of saying take the derivative, right? If you're looking for a function whose antiderivative is that thing, take the derivative of that thing, so you get the function whose antiderivative is that thing. But it seems like the longest way you could say it, maybe. I imagine he had a point. Maybe I don't know what the point was. Okay, so yeah, it's not my favorite example. So let's change this up. Yeah, yeah, yeah. I'm gonna make this real basic. So let's say we've got a rectangle. And this side length is x and this side length is y. And I think you all know that the area as a function of x and y is just x times y. Cool. Now let's say we know some things. Let's say that, let me see. Let's say that, so let's start off with this presumption. X and Y are changing. We have some interesting rectangle where the length of one side and the length of the other side can just kind of lengthen or decrease at will because it's a sentient rectangle that decides to be bigger or smaller. Okay, so X and Y are changing. Specifically, here's what we know. Sure. So if at a certain moment in time, X is sure 10 inches long and increasing at a rate of 2 inches per minute. And Y is 30 inches long and it's an inch and decreasing at a rate of 1 inch per minute. How fast is the area of the rectangle changing? Or even a more general question, is the area increasing or decreasing? I have no idea until we do the math. It could be increasing, it could be decreasing. No, I don't have a good guess because the rate of increase is a little faster, but there's less length to be increasing there, so it could really go either way. So how do we do this? Well, the idea is that area is a function of both x and y. So we're going to draw a little mapping, is what we usually call it. So area depends on both x and y. But x and y both depend on the third variable we haven't mentioned. They both depend on time, right? X and y are changing as time goes on. They both have rates of change, aka derivatives, that are mentioned in the problem. We know that x and y are both functions of time. So we want to find how the area is changing, how fast the area is changing. In other words, we want to find the derivative of the area function with respect to time. So what we really want is we want to find dA dt. And yes, I said d and I wrote d because even though we don't know what it is, at the base level, this area is a function of just time. If we knew more things, we could write out what it actually was, but we're not going to do that because it's not really the point. So we're going to find all of the pathways that get us from area to time. And it looks like there's two. One of them goes through x, one of them goes through y. So we're going to say that the derivative dA dt is equal to, well, this pathway first. When you're going from a to x, it's the derivative of a with respect to x. I should really say the partial derivative of a with respect to x because at this level, a depends on two different variables, and so it's a partial derivative. So it's going to be del a del x times the pathway from x to t is going to be dx dt. Similarly, we're going to add and take the other pathway from a to t through y. So it's going to be del a del y times dy dt. So this right here is the chain rule. If you're trying to find the derivative of a function, you have to find all the pathways to get you kind of from the top function to the bottom level variable. And then every time you go from one level to another, it's a derivative. So from a to y is a derivative of a with respect to y. From y to t is a derivative of y with respect to t. You don't really need to worry so much if they're partial derivatives or regular derivatives. No one's looking at your work and like, is that a del or a d? I can't tell. No, no one cares. But I care. So I'm trying to write the right things. But if you write the wrong thing, it's not a big deal. So let's see what we've got here. So dA dx, well, my function is a equal to x times y. And I said d, but I wrote del a del x. The partial derivative of a with respect to x is just going to be 1 times y, or just y. Dx dt was told to us x is increasing at a rate of 2 inches per minute. So dx dt is 2 inches per minute. Normally I would just write 2 and worry about the units at the end. But here I want to show you the units to show you that they do work out. Similarly, dA dy, the partial del a del y, the partial of a with respect to y is going to be x. And dy dt, well, we were told that y is decreasing at 1 inch per minute. So it's not 1 inch per minute, it's negative 1 inch per minute because it's a decreasing rate of change, not an increasing rate of change. Right? Y is getting smaller every minute, not larger. Negative 1 inch per minute. So that looks terrible. There's a negative 1. Apologies. But then we need to plug in the values that we have, right? Because we know that in this example, we're looking at the moment when x happens to be 10 inches long and y happens to be 30 inches long. So we end up getting y is 30 times 2 inches per minute. Sorry, 30 inches times 2 inches per minute plus x is 10 inches times negative 1 inches per minute. So adding these together, let's see, 30 times 2 is 60, 10 times negative 1 is negative 10, 60 minus 10 is 50. So it's increasing at 50, and the units are inches times inches per minute, so inches squared per minute, as you would expect for the rate of change of the area of something. So this rectangle is definitely increasing in area at the moment that we're looking at. Cool. So I will point out there is another example that I might encourage you all to read that is on Grant's website, just so you can all see where to find that. So here's Grant's website. If you look down here to the chain rule stuff, this first example is worth reading, but the numbers are atrocious, kind of like the previous thing we did. So I would recommend reading this because it's more of a real world example, like with actual PV equals nRT stuff, like pressure, volume, temperature. It's, I think, something that actually makes more sense maybe, but I didn't want to do it because the numbers are gross. So you should read that when you have a second.
Similar to chemistry, what did we do to conversion factor?
What conversion factor are you talking about?
Like the units.
Yeah, the units will totally work out just fine, the way you'd expect them to. That's in Grant's website. Oh, that example might also be in the book. Oh, it is? Cool. Then you look at the book too. But I think Grant does a good job of explaining it there. So that said, what time is it? 1:54. Let's do one more example. A more kind of typical just math for the sake of math example, which is usually what I'm doing because I like math. So let's say we have the following function. Suppose f of x comma y is equal to y cubed times e to the 4x. And we have that x is equal to cosine of t and y is equal to sine of t. I want to find df dt, the derivative of f with respect to t. And although you don't have to draw it, well, in fact, we're going to do it, yeah, we'll do it 2 ways. So first, we're going to do it maybe an older way where we're going to just write f as a function of time, or t, and then differentiate. Which isn't always something that's possible, but something that we can certainly do here, right? We can rewrite f of x, y equal to y cubed times e to the 4x. We can rewrite that as f of t equal to, well, replacing y with sine of t, we have sine of t cubed. And replacing x with cosine of t, we have e to the 4 cosine of t. And now it's a function of just the variable t. And we can find the derivative in the usual way, using the product rule and the old chain rule. Product rule. Okay, so let's see. Derivatives of stuff cubed is 3 times my stuff squared times the derivative of that stuff times the other piece, e to the 4 cosine of t. For those of you that like this kind of notation, I'm thinking of this as like my g, and this is like my h, and here's my g prime multiplied by my h left alone, and then we're going to switch it up. We're going to leave g alone, so we have sine of t cubed times the derivative of e to the stuff is e to the stuff multiplied by the derivative of that stuff, which is going to be 4 times negative sine of t, or negative 4 sine of t. That's my g times h prime. At least for this one, not incredibly terrible. Like, not nice at all, but reasonable in the realm of taking derivatives of things. Let's look at doing it the other way. So the other way meaning using the chain rule. The new chain rule. So again, you don't really have to draw this little mapping. I like to. I really do like to. Like, I found this fun when I was taking calculus back in the day. So same kind of, I should point out, not every mapping is going to look like this, where your top function depends on two variables, and those two variables each depend on the same one variable. We'll see other examples next class where it's a little bit different. So here, we're going to say that df dt is going to equal the partial derivative of f with respect to x times dx dt, the derivative of x with respect to t, plus the partial derivative of f with respect to y times dy dt. Let's go ahead and take a look at it that way. So, looking at my original function, del f del x, the y cubed sticks around as a constant multiple, and the derivative of e to the 4x is going to be e to the 4x times 4 times dx dt, which is negative sine of t, plus del f del y, which is going to be 3y squared times e to the 4x times dy dt, which is the derivative of sine of t, which is cosine of t. Now, I will point out, technically not the same until we plug in what y and x are equal to. I don't really want to, but I will this one time, because I like you guys. So if we plug in sine for y and cosine for x, we get sine of t cubed times e to the 4 cosine of t times 4 times negative sine of t plus 3 times sine of t squared times e to the 4 cosine of t times cosine of t. And even though things are written in slightly different order, it's still the same result. I have a sine cubed times an e to the 4 cosine of t times a 4 times negative sine of t, or negative 4 sine of t, plus 3 times sine of t squared times cosine of t times e to the 4 cosine of t. So the chain rule really does actually work and gives you the correct result. Right? You could have done it this other way, which maybe wasn't too terrible, but this way is actually going to be what we usually do because well, usually we don't go to this last step. Like, yeah, we all can plug in sine for y and cosine for x, or whatever the functions have to equal to, and see that you get the thing. But that's not really necessary for us all to be like, yeah, we took the derivative and sure, plug it in if you need to, or don't if you don't.